We're going to start with chapter 8 about momentum and collisions. Okay? These two topics, they come together, like the energy and the energy together with momentum. And we are going to test in the coming exam both topics together. Now, the momentum that we are going to talk about today, it is called linear momentum because my object is moving in linearly or in a straight line. Okay, and this is to differentiate between angular momentum, which we will study later. Okay, then today our topic is just in linear momentum, where the object moves in a straight line. Now we define linear momentum as inertia in motion. Then I have actually a mass that is inertia in motion. I have an object that is moving. Inertia means mass and motion means velocity. And based on this, we're going to define momentum P as m times v. Now, mass is a scalar, but momentum is a vector and velocity is a vector. Then momentum, it's a vector quantity. It has the same direction as velocity. Then if the object is moving to the right, momentum is positive. If the object is moving to the left, momentum is negative. Then it has the same direction as the velocity, and to calculate what are the units of momentum, we'll say P is mass kilogram and velocity, it is meters per second. Then this is the unit used for momentum. It doesn't have a special name, and it can be written like this. It can be written as this. Now, most of the time, I have to worry about momentum of a system, not only a single particle. And here, I will say, in general, let's say have mass 1, and I have the velocity for it, m1, and any mass 2 moving with velocity v2. Okay, now what I can say, I can calculate total momentum as mass 1 v1 plus mass 2 v2. And of course, we can generalize to as many particles as we have. Now, something that was brought by Newton's first law, Newton's second law, is sigma F equals m times a, where a, of course, the acceleration, sigma F is the net force. Then we can here say sigma F equals m delta V over delta T. And then here I can say this is m V final minus V initial, because this is the meaning of delta V. And from that, we can say sigma F should equals mv final minus mv initial divided by the time. Now, that one, if you recognize, it is the the final momentum. This is the initial momentum over time. Then actually this is the change in momentum divided by time. And this is really what is very important. I will say, this is, we call it a second or like equivalent statement of in Newton's second law. And it's telling us very important thing, which is in order to change the object's momentum, you must apply a force. Then if that force, and here we will say if we have no external forces, okay, which means sigma F equals 0, then delta P over delta T is 0, and this means that total linear momentum will not change, which means that total linear momentum is conserved. And this is the conserved, and this is the conservation of linear momentum. Now we will deal with, okay, situations where momentum does not change, and we will see that we can apply conservation momentum. But just I want to tell you, like here, there is something called external forces versus internal forces. Now what I'm talking about here is what external forces. Then if, let's say, I have two masses here, and this is one system, I can consider it one system. Okay, the external force is 0, but that doesn't mean that we don't have internal forces. But when we sum all the forces, these are, because they are equal in magnitude, opposite in direction, they're gonna cancel because they are internal forces. Now, in general then, when that applied force is 0, what I will get is momentum should be conserved. What does that mean? That means when momentum, when the condition is applied, when momentum is conserved, okay, this means I don't have external forces, then there is no push, there is no pull, there is no friction, there is no external forces at all. Then Pi equals P final. And then I can say M1 V1 plus M2 V2 equals M1 V1 prime plus M2 V2 prime. What does that mean here? I'm telling you that initially this was the position, the situation. This is V1, this mass 1, and maybe this is V2. I don't care now, it is in general, right? M2, and this is before collision. After collision, the velocities, because of the collision, they were changing. And again, I can't say until I know what are the masses, what are the velocities before. Now, if I have, as I said, external forces, that law does not apply, then I can't apply conservation of momentum. Now I'm gonna show you how we are going to deal with situations when the external forces are not zero. Which means here, I don't have the case where momentum is conserved. Now, we can say that sigma F equals delta P over delta T, and this means delta T times sigma F equals delta P, and I can define now a new quantity. I will call it impulse, and that impulse is sigma F, the force times time, and that equals change in momentum. Then the change in momentum equals impulse. Now the impulse here, we can give it in Newton times second, because it is basically force times time, and in the same time it equals, and it is equivalent to kilograms meters per second. Then the two units can be used to describe impulse. All right. Now, okay, I want to introduce an example here. Talking about in car accidents, then I will say in any car accident, the driver, if I assume good driver, moving with 65 miles per hour, and if there is a hazard on the road, he or she will stop. Then finally will stop. Then I will say delta P, the change in momentum, is constant. The reason it is constant, that it is the same if the driver the same, I will say, whether the driver is wearing a seat belt or not, because that depends, the delta P here depends on the initial and final velocities, right? And that is mv, let's say, prime minus v, where of course we're using the prime for the final velocity. Now then, that delta P, which is Oh, let me remove these here. Okay, then I will say delta P which is M, delta V is going to be the same, equals the impulse, which is going to be the same, because the impulse equals delta P. Now, I will say here, I want to compare with seat belt, and here without seat belt. The force with seat belt is going to be small because the time is really extended, versus if without the seat belt, the collision time is going to be short, and then the force will be large, so that they will be equal. Because I will say this is impulse 1 should equal impulse 2. Then I can increase the time of the collision so that I will make it safer for me, which is wearing a seat belt or not having a seat belt. Another maybe thing I want you to think of here, it is again, this is my car, and I am a good driver again, I'm gonna assume. And then I have noticed there is a kind of a hazard on the road and I need to stop. Then there is here a stack of hay or a haystack, or number 2, there is a wall of cement. And I have a choice either to hit this or hit this. And remember here, my final velocity is going to be 0. Now, in order for me to actually to compare, I need to think in order to decide first, where is delta V greater? Is it number 1 or number 2? When I hit my change in the velocity, is it the same? Is it a greater with the wall cement or the stack of hay? No, it is the same. Because my final and initial are the same. Number 2, what about when delta P is greater? Is it scenario 1 or scenario 2? And since delta P equals mass times delta V, I will say it's the same. And number 3, when the impulse is greater, and then I will say none, because they are both the same. Delta P equals impulse. Finally, I'm asking you, when the force is greater, 1 or 2, and of course 2, force is greater here because the time is shorter. Okay, then when I hit the cement wall, the time is gonna be shorter. Now, also again, we can say this is F delta T equals F times delta T. Now, it is sometimes a good practice to calculate the impulse using the area under the curve when we plot, and maybe it's any type of graph. Then you will find the impulse from the area under the curve or the graph. By the way, impulse, we call it J, like we give it J. Now I can easily here, let's say this is 13 newtons, and this is, let's say, 9 seconds, and this is 18 seconds. I can say here that the impulse equals 1/2 9 seconds times 13 newtons plus 1/2 times 9 seconds times 13 newtons, and I will be able to calculate what is really the total, and that is going to be your impulse. Here I will say, now what if I have momentum is conserved, conservation of momentum? This is the case when I have no external forces. And we can solve this type of problem here, where I have mass 1 is 0.5 kilograms and V1 is 2 meters per second. And I have mass 2 as 0.3. This is before collision. And when the second mass is moving to the left, like in here, you're gonna give it a negative, don't forget. And then I want to find what is really, this is mass 1, what is my V1 prime, and this is V2 prime, which is, I don't know, mass 2, and this is after collision. Okay, after collision, this one was given as 1. Then the question is, what is the velocity of mass 2 after the collision? Remember, here we are going to add momenta as vectors. Okay, then M1 V1 plus M2 V2 equals M1 V1 prime plus M2 V2 prime. and I know that this one is 0.5, this is 2, this is 0.3, and don't forget the negative for mass 2, and the final 0.5 kilograms times 1 meters per second plus the 0.3 kilogram times the V2 prime. We can say that the result of this calculation is going to be given as this. Then this is the direction for and the velocity for the second mass during the collision. Now, we define here collision an event that is going to include interaction between two objects for a very short time. And when they are going to hit each other, we can say force from 1, 2 on 1 should equals negative the force from 1 on 2. Now we have many types of these collisions. The first one that we are going to introduce now, it is called elastic collision. Now in elastic collisions, these are happening between marbles, billiard balls. Okay, and here I will say momentum is conserved in all types of collisions. For example, we will do now head-on collision, and this is considered to be one dimension. And we will do, of course, two-dimensional. Now, first, you should apply conservation of momentum. And this is translated to this equation, m1 v1 plus m2 v2 should equals mass 1 v1 prime plus mass 2 v2 prime. The second one, it is kinetic energy is conserved, and here it is 1/2 m1 v1 squared, this is the kinetic energy, plus 1/2 m2 v2 squared should equals 1/2 m1 v1 prime squared plus 1/2 m2 v2 prime squared. Now I can derive an equation from both because the second one it's sometimes difficult to use, and that one is gonna be v2 prime minus v1 prime should equals minus v2 minus v1. This is, I'm gonna use this one because it's much easier. Let me show you how. Let's have this example here. Where the question is gonna say or state that it is an elastic collision. And then here I have mass 1 as 0.5 and V2 is negative, like the same exact numbers from the previous one, but I'm gonna assume that this is elastic. Now, in order for me to calculate here, I will say here I don't have any like velocities after given. Then the question is asking about the velocities of the two masses, assuming that this collision is elastic. First, I will apply conservation of momentum. I will get one equation from this. Just to plug in the numbers and make an equation that having the two velocities after collision, because these are really my unknowns. As a result of this, I will get an equation 0.4 kilograms meters per second equals mass 1 V1 prime plus mass 2 V2 prime. This is my number one. I will use this equation now, the second one. I will not use the energy. Like you can see in your textbook, sometimes we did use the energy because it's easy, but in my situation here, it's not. This one is much easier. This relation now is gonna give me a relation between the final velocities, which I can use it to plug in the first equation. Then now here, what I can do is I can say that V2 prime, it has a relation with V1 prime, and this is the relation which I can bring it here and solve for one variable. And I have two equations, and I will be able to say 0.4 kilograms meters per second should equals 0.5 V1 prime plus 0.3 V1 prime plus, and that is gonna be 0.8 V1 prime, and finally 0.8 negative 0.8 equals 0.8, and my V1 prime will be negative 1, and based on this value I will be able to find the second one as 3. Okay, then this is one strategy of solving problems related to conservation of momentum. Thank you, and I will see you in another